Hey everybody. So, this week, what we're going to be talking about, we have a few lessons to cover, and all of the lessons are going to be on the same theme. And that theme is the confidence interval of a parameter. Accidentally pasted something else. We'll see that come back in a bit. So, let's talk about the words that we see here. We have the word confidence interval, or the phrase rather, confidence interval. We will talk about what that means in a second. And we also have the word parameter. That word looks familiar. We learned earlier in this course that a parameter is a calculation made from a population. And not only did we learn that it was something from a population, but because of the nature of a population, which includes everything, it is very difficult for us to get a parameter. But we've seen some parameters rather recently in our course. We have used them in our projects. For instance, when I did my example video with the Kevin and Shaq project, I took my height of 70 inches and I converted it to a z-score so I can go use the standard normal table to answer some questions about people that were taller than me or people that were shorter than me. To convert my x score of 70 to a z-score, I had to use this formula here in this box. The formula is x minus mu over sigma. Remember what these things mean. Mu represents the population mean. And I used the population mean of 63.5. And I used that because that is the number that I got from the link that I put on Moodle for the average height of women in America, 63.5 inches. So what we're going to be looking at in this lesson is, think about the question. Do you think it is very likely that the population mean height of women in America is exactly 63.5? Or do you think that it is very unlikely that the population mean height for women in America is exactly 63.5? Let me phrase that differently. Do you think it is very likely that the average height of all women in America is 63.5? So I've made a number line because this is a continuous variable. So you see it is important for us to think about, remember the difference between discrete and continuous variables, because I could not make a number line for a discrete variable. Say I was talking about the number of cars that the average American had. We wouldn't make number lines for that. Do you think the probability that the average height of all women in America is exactly 63.5? Or do you think it could possibly be 63.287 inches? Or do you think that there's a good chance? Do you think that there is a good chance that the true population mean of all women's height in America is maybe not 63.5, but maybe 63.52876 inches? You see what I'm saying? It is very unlikely that it is exactly 63.5. They would have to make sure they got the height of every single woman in America to get this data 100% accurate. But I hope you would see that there is a pretty good chance that it could be the blue number. It's a good chance that it could be the orange number. It's a good chance that it could be the 63.5, but it's not a good chance that it is exactly the 63.5, right? To just pin it down to that one number. What we would feel more comfortable saying, and so that might sound confusing. I said it's a good chance, it's not a good chance. What I'm trying to explain is that although it is unlikely that it is exactly one of those numbers, it is very likely that, say, it is any one of these numbers that I highlighted in blue. So I might not feel comfortable. I might not feel confident. Confidence intervals. I might not feel confident saying that the mean height is exactly 63.5 for all women, but I may put money on, or maybe I shouldn't say put money. We're not talking about gambling here. But I would feel very confident saying that it's between, say, 62.98. I'm just making up some numbers where this interval that I highlighted ends, and maybe 64.287. Just made up some numbers where that could be. So it's very difficult for us to pin down parameters because population data is hard to get. But once we have a very good estimate, that word's going to come up again this week. Once we have a very good point estimate of what it could be, we could then give ourselves a little bit of grace, a little bit of wiggle room to move over to the right a bit and to move over to the left a bit, and then be very confident, maybe 90% confident or 95% confident or 99% confident. We'll see those numbers show up again this week, that it is between these two numbers. That's what a confidence interval is. So we just looked at an example of finding a confidence interval for a mean. Because remember, that 63.5 was the average height of women, well, the alleged average, right? The average height of women in America. This is for a mean. So I just gave an example of finding a confidence interval for mu, the population parameter. Remember, we use Greek symbols for population data. We're going to have two separate lessons for confidence intervals on the mean, because the way that the formula that we use to find our wiggle room, we have to use a formula to find that wiggle room. The formula that we use to find the wiggle room depends on if we know the population standard deviation sigma, which is very unlikely in real life because it's the same issue. Hard to get population data, or if we do not know the population, if we do not know the population standard deviation and we only know the sample standard deviation, which is S. So there's going to be two separate lessons for confidence intervals for mean, depending on if we know the population standard deviation or if we don't know it. And after we've seen both lessons, I'll throw in some examples where they're mixed up to make sure that we do know how to distinguish between which formula we will use depending on the situation. The second type of confidence interval we are going to look at is a confidence interval for a different type of parameter. And to refresh our memories, I'm going to go back to Moodle. We had a project on binomial distributions, and I probably should have entitled this project like Cigarette Smokers in America or something. But in this project, you explored different questions about the probability that certain numbers of Americans smoke cigarettes or didn't in a certain group, right? But you had to start this project by answering this question: what percentage of US adults smoke cigarettes? And you Googled that question and you found 12.5. Look right here. You know what my question is, I hope. My question is, how likely do you think that the percentage of Americans who smoke cigarettes is exactly 12.5? Not 12.52, not 12.5387, not 12.499962211. Exactly 12.5. It's very unlikely. In fact, look at what this says here. In 2020, an estimated 12.5%. That's an estimate. That is an estimate for a population parameter. That's exactly what we're talking about in this lesson. We're going to find out, how do we get these estimates? How do I get the point estimate for that population parameter, which is going to have a symbol? We'll learn that symbol in a bit. It's going to be P. And then once I know my estimate, which is very similar to like what we were doing up there with the mean, I would feel very confident to maybe say I'll give myself a little bit of wiggle room to the right and a little bit of wiggle room to the left to say that it is on this interval, that the actual true population percentage, because remember, here we're talking about percentages, because I looked up the percentage of Americans that smoke cigarettes. I didn't look up the average. I didn't look up the average of Americans that smoke cigarettes. And I hope you realize that question doesn't even make sense, which is why it is important that we do know how to distinguish between our different types of statistics, right? Or different types of calculations that we can make. Because the formula will be different if we are doing a confidence interval for a proportion, percentage, same thing, versus if we are doing a confidence interval for a mean. So that is a quick introduction to what we will be doing. And now let's go learn. We're going to start with the mean, look at both cases, and then we will go look at the confidence intervals for proportions. And I just thought of one more thing before we go, keep in mind that it is very difficult to get population data, as we have said, but I've made this comment several times now about how confident we can be that it falls between those two numbers, that it falls somewhere in that interval. We can be, as I'm sure you would imagine, you can be more confident if you have a better point estimate. So if you are starting at the best place in the middle before you start giving yourself a little bit of wiggle room, then you can be more confident. But to start at the best place in the middle, to have the best point estimate, to have a very good point estimate, you need to have a very good sample. We talked about the importance of sampling earlier in this course and different techniques that you can use to get your sample. The better sample you have, the better point estimate you have. And one thing that makes a good sample is a large sample. The bigger your sample, the better your sample is, the more representative it is of your population. So one of the other concepts we'll be exploring this week is, well, how big of a sample do I need to be able to get some really good data? How big of a sample do I need to be able to be 99% confident? All right, what's the smallest sample I can get away with to be 99% confident? Because it is very expensive to collect data. I mean, imagine if they were trying to collect this data for the population mean height of women. Imagine how much time and money it would take to get every woman's weight or every woman's height in America. That's going to be very expensive. It's going to be very expensive. So one of the things we'll be exploring is, well, what's the smallest number of women that I can sample to be 99% confident? So we'll also be finding minimum sample sizes, and we're going to learn all about that in the next few lessons.